Yeah, good morning. This is the first in a series of meteorology workshop. That's meteorology and climate science workshop. That's going to be organized between Ghana Meteorological Agency and KNUST. This workshop has been made possible by African Swift. African Swift. That's science for weather information and forecasting techniques. This project has really given the opportunity to Ghana Meteorological Agency and the KNUST, the training institution, to work together. Now, on today's workshop, my topic that the organizers provided was for us to look at is mesoscale numerical weather prediction, a solution to tropical weather forecasting. Is it a solution? Now, I want to start this way. First of all, we want to look what is the tropical weather forecasting? What is it all about? And then here, we also want to look at the challenging issues that really relates to tropical weather forecasting. Then we also want to look at numerical weather prediction. And then we'll look at the background. And here, since this is the key topic, my focus, I will have a lot of things to say here. Look at the challenges, some of the numerical weather models, their merits and demerits. And then also I will then show a sample studies within the tropics and conclude. Now, tropical weather forecasting is prediction of the state of the atmosphere in the tropics. And this prediction, as we know, within a day to about a week. This is what we expect. And we know that as it gets closer to the week, it becomes the forecast become poorer. So the forecast become poorer as it gets close to a week, and better within a day, and could even be better within for hours. So we can even bring it to say a prediction of the state of the atmosphere within some hours to about a week. That is how we look at it. Now, one key problem about the atmosphere is very chaotic. Problems in the atmosphere within the tropics changes within a few minutes to hours. And that is one challenge that forecasting face. And this, of course, impede on the accuracy of forecasting. Now, to have a good forecast, there are certain key things that you need. You need we need a climatological data. We also need daily observational weather data. And this data should come from both ground-based stations as well as upper air observations. You need all these. These data are very important if it comes to predicting tropical weather or going through tropical weather forecasting. Now, there is also the need for us to do data assimilation. Now here, the information gained from observation become critical. And so the information gained it's really input into a model, and these model results comes out. And again, it goes through a process through the same assimilation, and at the end, an output comes out. And this output that comes out becomes the forecast. However, these outputs has to go through verification. So there's a verification process that goes through. So what you see here is just a simplified model showing this. Now, the challenges in the numerical in tropical weather As I started, the tropic usually have a relatively homogeneous air mass and also fairly uniform distribution of surface temperature and pressure. And therefore, local and mesoscale effects are more dominant than synoptic influence. This is an exception of what tropical cyclones. For example, surface temperature and pressure can change quickly within a convection and also in sea breeze. Additionally, there is also a challenge in sparse network. As we know, there's data scarcity becomes a problem. We have observational data within the tropics is really very scarce because this is the part that we are located. And if I provided a data network within our continent, it will amaze you that the resolution is very, very poor. And so that remains to say that the vast region of the tropics, in particular the oceans and parts of Africa, the best way to do observation is using satellites. However, these satellite data also have their own challenges. Satellites, for example, if it's a polar orbiting satellite, which usually are sun synchronized, these satellites these satellite informations the overpass are usually the best overpass you can get is about twice in a day. Sometimes it can be even once in 3 days, once 2 days, and so on and so forth. So this leaves us to have a large data gaps. However, recent increase in geostationary satellites have become the solution to minimize this, but that can also not provide all the data that we need. And so this data gap still remains a challenge. The other thing that we have to see, which is a challenge, of course, is also computational powers. And of course, we also talked about, in general, stability of energy, or in other words, supply of energy to really provide consistent runs of this model. This is also one key thing which we will talk within this. Now, what do we mean? What is the numerical prediction model? This has been the key rapid improvement in this particular thing. What we know is that the numerical models have worked extensively in the mid-latitude, but within the tropics, we are yet to fully explore or use these to enhance our weather forecasting. Now, what you see here is a numerical model, prediction model, and this model has a number of processes that goes within. As we can see, we have processes like data assimilation. We have the model forecast run itself. We have post-processing. And before we have the weather forecast. So these processes are, as you can see, this is cumbersome and really time and computational and energy expensive. Now, in order to do this effectively, we also need observation. I have already mentioned that we have challenge in the observational data, which are, as I indicated, we scarcely have currently upper air observation. Upper air observation comes in only within times that we have projects. However, we have a number of ground station observations, but this is also, there's still room for improvement in this direction as well. Already, there are information from previous forecasts and also from the experience from the forecasters themselves become very critical. A very experienced forecaster, in general, also have a hand in providing a better forecast compared to a novice forecaster. So the more people stay in the operational centers, they develop their own techniques and better way of getting information to support what will come from the numerical models. Now, as I mentioned, there's also this data comes in order to get effective data, we'll need to do a data control, or in other words, quality control for the data. And this means that all these processes, within this process, one key thing that you realize is that all these processes them itself will have some challenge. That will mean that there might be some errors, both systematic and some of course random errors that will come in, and this itself is a challenge to weather forecast. So then it affects the accuracy of the forecast that will really be provided. Now, the numerical weather models itself will have to work on some physics laws, the conservation of momentum, continuity equation, that conservation of mass, and then conservation of energy. Aside, also, there's also have to be issue on parameterization of the atmosphere processes, process like cloud formations. So then the cloud physics comes in. We also have to look at radiative processes, boundary layer processes, including the earth surface processes. All these, such as soil moisture, among others, are all critical information that are required in these numerical prediction models. What are some of the things that these models outputs produce? We are able to get information on wind, temperature, moisture, pressures, among others. And some of these information are usually provided, as in the case of Ghana Meteorological Agency, 24 hours. We must say that there has been a very tremendous improvement in the weather prediction, or in other weather forecast as given by the agency in its last days or the last years. This has really been as a result of very effective and efficient staff that are working so hard daily to combine various ways, including numerical weather informations, to really give out these accurate weather forecasts. Now, in short, what then is a numerical prediction? So here, as from all that I have said, it means that the numerical prediction uses numerical methods to solve equations governing the atmosphere motions, processes, as well in order to obtain forecasts. And this forecast can be from hours to approximately a week. This is what this is about. Now, almost every model uses strictly different sets of equations, depending on the numerical models. As you will see, soon we'll compare some of the models. You realize that most of them, there are key processes that are also different. And then what the purpose of the model is about, the resolution of the model is also a critical thing. Now, one process that is a challenge within the tropics is the micro scale, the meso scale and the micro scale processes that really influence the weather within the tropics. It's also one thing, including other processes which we're going to highlight in this lecture. Now, there's also the need for different atmosphere processes to be considered. Of course, there's also the numerical, where there's also different time or spatial scales that are used for this in these models. Now we have ambiguities and uncertainties in also formulating these models. And then another challenge will be tailoring these to different uses. That is also one key challenge. Now, within the NWP models, one key thing that we have to realize is that we need to provide both initiation, verification of data, in order to, and in addition to verification of the forecast itself. Now, what we will see is that one key process challenge that all numerical weather models will have is the issue with the parameterizations. And this comes as a result of the processes that are mentioned in the atmosphere. Convective processes, where we are looking at issue in the boundary layer, processes involving the boundary layers, radiation processes, the surface, the processes involving of the heterogeneity of the surfaces, so surface information itself. All these processes provide a challenge to the model. In addition, there is also a transfer of systematic errors, as I mentioned, that it goes through different processes. The simulation processes themselves alone could carry out some process. And of course, there could be an error from the previous forecasts or itself also transferred into a new forecast that will have to come out. So these are all, and many are the challenges that we face, including the data, availability of data. Now, there are two factors that we have to consider here. Despite several decades worth of advance, we still do not know, and probably never will know, what is the best model configurations. So configuration of the model itself is a problem. It is not immediately clear that one does or what should exist. So the model configuration itself at every time is a problem. You need to work on regularly in order to really come out with the model configuration through several simulation processes in order to come out. Even that, because the atmosphere itself continues to change within the tropics, it means that this process itself has to continually be updated in order to meet these challenges. So even if we could identify a best model configuration, all models will provide imperfect forecasts that even if they verify well, they are likely obtaining a reasonable solution for at least, especially a wrong reason. In other words, the ability to predict does not necessarily imply predictability. Yes, there will be ability to predict, but is what we are predicting, is that right? That becomes also a question. One key problem that also exists, which I have not mentioned, is really the kind of models that exist now. In most cases, we try to adapt a model that is meant for high latitudes for tropical situations. That itself is also a challenge. Very recently, there have been few models that has been really developed purposely to really support that have parameterizations that have tropical inputs. However, these models themselves also sometimes have challenges, reasons that have been mentioned earlier. Now, types of model. The numerical models, there are a number of numerical models, but we want to really restrict ourselves to few that we'll discuss for the purpose of this lecture. Now, the capability of a numerical model to accurately predict tropical weather depends on the type of the model. Now, how the model equations are solved, how the data, so in general, the approximations, that necessary approximations in the model equations, availability of data, types of weather features that can be resolved by that model. These are key issues that are considered. A grid point model actually represents the atmosphere in three-dimensional grids. As you can see here, this is the three-dimensional grid as seen in this particular image here. This can provide high resolution, a high horizontal resolution for regional and mesoscale application, but do not need to transform physics calculation to and from the gray space. As the physicist operational models becomes more complex, grid point models are becoming computationally competitive, in general computationally expensive. Non-hydrostatic versions can explicitly forecast daily details of these convections, given the sufficient resolution and details in their initial conditions. Now, some disadvantages of this. As you know, finite difference approximations of the model equation introduce significant amount of truncation error. Now, a small scale noise accumulation when equations are integrated for a long period. The magnitude of the computational errors is generally more than the spectral models of comparable resolutions. The other thing is that boundary conditions errors can propagate into regional models and even affect the forecast scale. So non-hydrostatic versions covers only very small domain and also short forecast periods. The other part that we can have is also some of them that are hydrostatic models. Now, for hydrostatic models, the most great point models, all spectral models in this current operational numerical are hydrostatics. And this means that no vertical accelerations are calculated explicitly. So the hydrostatic assumptions are valid for synoptics and also planitic scale systems. And for mesoscale phenomena, an important exception is the deep convections, where buoyancy becomes an important forcing. So hydrostatic models account for effects of convective using statistical parameterization approximations. And the large scale changes in temperature, moisture caused by these non-hydrostatic processes. So then there's also a challenge. This cannot predict vertical accelerations and can also not predict details of small scale processes associated with this buoyancy. However, the advantage is that they can run fast over limited area domains and provide forecasting in time for operational use. So the hydrostatic assumption is valid for many synoptic and sub-synoptic scale phenomena. Now, currently, most non-hydrostatic models are grade point models, and they are generally used in forecast or research problems requiring very high resolution, from about a tenth of a meters to few kilometers, and they cover relatively small domains. So non-hydrostatic model can explicitly forecast the release of buoyancy in the atmosphere and its effects on development of deep convection. To do this, non-hydrostatic model must include additional forecast equations that account for vertical acceleration, vertical motion directly, and rather than determining vertical motion diagnostically from horizontal divergence. To account for vertical motion and buoyancy properly, non-hydrostatic model must include a great deal of detail about cloud precipitation processes in their temperature and moisture forecast equations. Since hydrostatic models do not have the vertical motion forecast equation, none of these processes can directly affect vertical motion in their predictions. Now, in comparison, as you realize, one disadvantage of non-hydrostatic model is longer computational time, since the model must finish running in time for forecasters to use model products. Hydrostatic models are more advantageous unless non-hydrostatic phenomena need to be simulated, or unless we are interested in very fine results around 10 kilometers. Non-hydrostatic models run at very high resolution characteristically and predict detailed mesoscale structures and associated forecast impacts on surrounding areas. Now, the disadvantages here is that it takes longer time to run a hydrostatic model with the same resolution domain size, used for limited area applications, as you can, for example, so they require boundary conditions. This boundary condition lack the structure and resolution characteristics of fields developing inside the model domain, and they may exert great influence on the forecast. They may predict realistic looking phenomena, but the timing and placement may be unrealistic. The advantages here is it can calculate vertical motions explicitly and explicitly predict realistic the release of buoyancy and account for cloud and precipitation process and their contribution to the vertical motion, capable of predicting convective, of course, mountain-related waves as well. The convective-scale model, which is the models that mostly are used today, significant process have been made in running these models over time. For instance, some of these models, we have the Cosmos DE model, the Aero model, the MET UM, the WAF. This can run at convective permissible scale for limited area predictions. The main advantage of these convective scale models is that more processes associated with convection are explicitly represented by the model numerics and rather than being parameterized. And one disadvantage of running a model with explicit convection at the scale between 4 to 10 is that the strength of the model convections tend to be unrealistically strong. So if you take a numerical predictive models for West Africa, number of these models I have shown, we're going to see an output of how these are able to predict, for example, a diurnal precipitation or rainfall over our region. Now, in doing this, it is important, all these models, it is important that physical ingredients needed to capture the diurnal cycle for convective parameterizations. And these include a period of shallow convection in morning that begins on the scene, is lower than the vertical turbulence. So also there's a well-defined transitions from the shallow to deep convections in the afternoon. And then, of course, there is also a convective triggering that links the scene to vertical kinetic energy that lasts, but not the least. There is also a reduction in the days of convection early in the day, but making changes in convective and treatment as a function of what? The height of LCL. Now, some of the models, as we can see, we compare this to actual observation. Now, TRIM provides the actual observation information here, and the others are models. And these are numerical weather models. Some are regional and some provide a global information. Now, as you can see, let's see, this is the observation, and then you see that some provides information quite close to observation. And one of such models, as you can see, the UK Met Office, but then looking at the nature, why is this provide that information? Look at where this at 6 o'clock, look at what is happening here. But however, this information is not that way in this particular case, as you can see. So in general, we can say that all these provide unrealistic informations at certain points. If you look at these informations here, what we see here, we see that the information here, you can see, again, this is again diurnal, but looking at it from this time, from the different model, again, compared to the observations. We see some agreement in some of the models, but again, we see the disparity. Why the choice of TRIM as an observation here, as you all agree with me, TRIM has shown consistently to be one of the best satellite products in the tropics or in our region that provides a realistic information to ground-based observation. Here again, we see daily to a week time scale. We see some of the observation either underestimating or overestimating at certain time scale. And similar is observed at this place. We see the same situation here. And here we tried to provide a smooth, trying to look at all, smoothing what we see already, trying to take the average observation as compared to the average of, again, the models, we again see a consistent under and overestimation in this particular case as well. This again is the same, this time in the Sudanal region. What we saw earlier was within the Guinea coast. And then we see the Sudanal region. Again, we see a consistent overestimation and again underestimation in some cases. This is the Sahel case. We see a mostly underestimation. The weather research forecast and forecast model, which is one of the key models we are adopting in the region. Let's see what happened. In WRF, which is a numerical weather prediction model used for atmospheric science research, actually, WRF incorporates the community model. These are just some of the informations on WRF. But in general, WRF, being a regional model, has shown a lot of strength in West Africa. The scale of WRF in predicting precipitation is quite good and have been shown to be very good. And so let's see some simulations from WRF. As you can see, this is stream, and then you see that the various versions of WRF has been used here, and you see that at least some versions come quite close to the observation as seen in a real measurement by TRIM. So we see that one key thing is that WRF has shown that it's able to really predict the rain belt. And then, of course, also the dry Sahel regions. These simulations have shown clearly. And as is seen in that particular here, you can see that within certain regions, we see very good as compared to observations. This Taylor diagram shows the various WRF and how well they have been able to produce observations, information. Now, one key thing that we'll see, although the scores, some appear to be good, but you can see that the experiment still needs some fine-tuning in order to improve the consistency in agreement with observation. Now, one key thing that remains is that there is still very high uncertainty in the numerical predictive models within the tropical, and these are things that we have to work on. So predicting severe weather in the tropics is still a challenge. We also see that running the models for very high resolution, we see the models face more challenge. There's more, because the models are not able to resolve convective processes, or in other words, provide unrealistic features. Currently, there's a way that we are a converting permittive model with an ensemble techniques to give a high resolution. It's a key thing to go. And this, we expect that if we are able to locally provide a more parameterization within the models, within the WRF, we have a high, the the results will be more promising. So the question one will ask here is that, is the mesoscale numerical weather predicting a solution to tropical weather forecasting? The answers are despite the challenge faced by the numerical models, they can be very beneficial for short-term forecasts. However, the forecast can be further improved. And as I mentioned, there is a need to improve the parameterization scheme. Of course, there is also the need to improve computational resource within the region and also observations. Improve observations that we use for verification of this model to minimize uncertainties that are characterized in or that are seen in this model. So we will say that there's still more room for improving predictive powers of this model in a region. Exploiting new observation, particularly remote sense platforms, and also developing improved data simulation methods. This will also make use of these observations in a data sparse region will be handy to improve bias in these numerical predictive models. We see that there's also the need to utilize this vast product that we have. There's also need to still improve, in particular, the use of nowcasting, in particular, the new data satellite geostationary, which I mentioned that these informations are very critical. And if this will help improve forecasting, and this information can also improve to improve the parameterization processes in these numerical predictive models. Thank you.
Thank you.
Yeah.
Thank you very much, Prof, for your wonderful presentation. Sorry for starting late. I think Prof will be moving for another meeting. If we have some 2 to 3 questions, Prof will answer the question, then we'll go to the next speaker.
Hand raised.
Okay.
Hello.
There are a number of people that they need to be and that they want to enter. Can you please do the?
Yes, we are admitting them, Prof.
Okay. Okay.
Please, any question?
Yeah, Bashir, this Emmanuel, can I ask a question
Yes,
quickly?
Dr. Yes, Prof. Doc, you can ask.
Okay, Prof, thanks so much for your presentation. That was an interesting one. I joined a bit late, so I'm not sure if it was mentioned at the beginning, but I just wanted to know, at the end of Prof's presentation, he had mentioned about some areas that ought to be improved with regard to the numerical weather forecasting model. So the wolf, for instance, that you demonstrated. So I'm just trying to ask if within your own work or in the project for which this presentation is being done, if there are specific work being done to improve on the wolf model, for instance, in the area of parameterization or any other aspect of it to improve on that. Can you share a bit of light on that?
Yes, I think that we actually using the WAF. Some of our own PhD students have made efforts to actually try to not do the parameterization. Firstly, trying to understand the WAF, and of course also try to do the configurations and to have, so they have done some simulations. We have our own work. We have done some simulation, but sorry, I have not shown any of that per the topic. However, I know that GMet itself, Bashiru, also have done, and some of his colleagues, they have also been doing some work. However, we have not taken any key issue in the parameterization, which we have to. So there's a need for us to really get the physics of WAF, and this is what I'm looking at, where we will look at, we'll take, for example, want to look at the boundary layer processes, the processes that are really inputted in it. We'll have a work that completely will do a thorough sensitivity study to understand that boundary layer processes within the model. And then so if we do all this, then this will better serve the purpose that we want WAF to do. Currently, WAF is doing well, but then we can improve in doing this. This is what I'm really looking at. But configuration for using WAF within the region, there have been some work done in that.
Yeah, thank you.
Basu, I have a question.
Okay, you have the floor, Johnson.
Thank you, Prof. Thank you for the good presentation. Prof, as you have mentioned, we have problem of getting good data, or we are in the region of data space.
Yeah.
How do we overcome these challenges of getting a data that fit into our model and serve as a initial condition, since that is the basis of getting a good forecast for from the model? Thank you very much.
Thank you. So one major issue that we have is that, for example, in Ghana, we have your agency, Ghana Meteorological Agency. They have been in charge of data collection, observation, etc. There are a number of projects also exist collecting data, etc. So one way to do this is that every data collection will have to, Ghana Meteorological Agency has to be aware. They have to be. So then, even after the project, those stations has to kind of be adapted, or in other words, incorporated into Ghana GMet's operational data collection process. And if we do this, it means that we are going to continuously decrease the number, or increase our spatial resolution for data collection. And of course, also going to help us have a long-term data that will be available for use. And also, so in general, almost all projects, especially if it's climate and climate related, all these data, it will be prudent that GMet is included in the process, and so that at the end, after Ghana Met, you take over to continue the data collection. So that is one way. The other way also has to do with, already we have the data that we have collected in the past that we have not been very cautious in collecting. We have to now improve in this. That means that there are situations where we are having data gap. We have to make effort to do a conscious data gap filling to really make sure that the data that we have, on other words, data quality control, we have to improve on our data quality control also, so that even the few data that we have can also be useful for the purpose. So we just have to be conscious. And also, we also need a data bank, which I'm thinking that we also have to have we currently will have to have a space in the cloud where we can call that space for Ghana, where this will have to be controlled by your Ghana Meteorological Agency, so that we can have all data, data that are collected, or what you have, all of them are deposited there for a purpose, and all this will help.
Thank you.
Others can also contribute to that. Yeah. This is my view.
Hello, Prof. Lamptey.
Yeah, I want to contribute to that.
Okay, you can contribute and at the same time share your screen for the next presentation.
Okay, so I think that in terms of the data, there is a need for some kind of legislation for any climate-related projects to involve Ghana Meteo right from the scratch.
Yeah,
because if you look at the Ghana Meteo database, there is a category of stations called experimental stations. When we created the database, we have synoptic, we have climatological, we have agro-meteorological, we have experimental, apart from the rainfall stations. And the experimental stations are for such things. So there's a need for some kind of legislation to involve Ghana Meteo in any climate-related. The project should not end before the data is given to Ghana Meteo. Ghana Meteo should be involved from the scratch. That's number one. Number two, Ghana Meteo has a lot of data on paper, and there is what we need is data rescue. We need to computerize that data. We need to digitize that data and computerize it. Thank you. Let me share my screen.
Yeah. Thank you, Prof. I think that is excellent. It's yes.
Can I go ahead?
Yes.
Thank you very much, Prof, for this wonderful presentation. And as you mentioned, it seems now there is so much data available, scattered across the country, or let's say the West African sub-region, for example, for our local consumption or for the parameterization which you are talking about. But I think the technology locally is the problem. For GMet, for instance, well, I think we will need so much assistance. So I would like to suggest, if it will be possible, then this time we could, because KNUST is in affiliation with GMet, if we could let PhD students or even master's students find means of using some of these data, like the thermo data, GMet, AWS, which has been acquired recently, as projects. They could use them as projects to see how best they can help GMet WAF models to help the country or to boost the output of GMet forecasts.
Yeah, I think, thank you. It's a line. I think that is one of the reasons for the seminar of this kind, so that we can develop, we have ideas, we can share, and so yeah, it's the right direction. That we serve as we want to be part of your research wing. You have your own research wing, but we want to be an affiliate research wing to GMet, and so as an affiliate research wing, we'll be happy to, because even you contribute to our student training. When they come on your site, we also expect them that they should. That's the last time I was there, I indicated that when students come, make sure one gain that GMet will make sure that you use some of their time to digitize the data, because they come there to learn. They should know how important data is. So data digitization is important as they come, as you move them around. They should do that. And then, of course, in terms of research, we welcome research topics. So I think that going forward, getting to time that we need student projects, we'll even write to you and request if you have some research topics that you want us to work on and so on, so that we can together do it. We'll do that as well. Thank you.
Okay, thank you, Prof, for your contribution, and thank you, Prof, for your presentation. Prof. Lamptey, can you share your screen for the next?
So, okay, so I'm presenting on seamless prediction, bridging the gap between timescales. Now, in terms of, if you listen to Prof. Amekudzi earlier on, he was talking a lot about some theoretical things. Anything we are doing, the scientific basis should be sound. And secondly, when we are talking about data and things like that, that means we are talking about failed experiments. We do a lot of, if you look at the models, which were designed, in fact, the calibration and things like that were based on field experiments in the mid-latitudes. That's why we are lacking in the tropics.
Yeah.
They don't work very well in the tropics, and a lot of things have to be done. Then another pillar, which is more or less a subject matter of mine, is a simulation. When we talk about prediction, the first thing that comes to our mind is simulation. So these are 3 areas which are pillars of the 21st century science. Now, the term, I put this up because people use prediction and they use forecast, but I think there's a difference between a prediction and a forecast. A prediction is a probabilistic statement that something will happen in the future based on today. That's a prediction, and it's normally it's dependent on initial conditions. Whilst a forecast, it's using the prediction to come up with, so it's a forecast is more of a judgment by a person. It includes other things. And to add to that, there is also a projection, which is what is used for climate change. And that's not a prediction. People say climate change prediction. It's not a prediction, it's a projection. It's a probabilistic statement based on certain assumptions. And climate prediction is normally a boundary value problem. So it depends on conditions, more than not initial conditions. And we end up doing these projections, we end up with scenarios, which we follow. We end up with scenarios, and the scenarios are more or less like storylines. They are like plausible alternatives of the future. So certain assumptions are made, and then we come up with some outcomes. Those are scenarios. So bottom line, what do we want? All this similar prediction we are talking about, what do we want? We want to be able to get a reliable, modern, and real-time service which will support our communities, countries, all scales, right? And also make us climate resilient and help us to achieve our economic development goals. We want forecasts at all time scales, space and time scales. And I know people want to stay in their house and know whether to rain in their vicinity or not. The science hasn't reached there yet, but that's something that we want, right? And there are people who are making decisions and developing strategies. So they are policy makers. They also need information about the future to incorporate that. And then we want early warning system. We want to reduce the loss of life and also damage to property. But to do that, we need an early warning system, which must be coupled with an early action. We normally say we need early warning, but it must be coupled with early action. Otherwise, the impact is not felt. Now, there's a lot of advancement. There's a lot of research going on, right now we have multiple sources of data, so many sources of data. We want to be able to integrate all these different sources to be able to cope with multiple hazards and then meet the well-being of society. We know that certain predictions are beyond our ability now. We need new predictive tools because we want to be able, like I said earlier on, people want to be able to stay in their house and still be able to know whether to rain in their vicinity. We need such things. There are many scientific processes, very small scale processes, which we still don't have a very good understanding of. We want to understand them. And then we want to be able to know or be able to have the ability to incorporate the weather information or weather and climate information into our decision making, not forgetting communication. There's the need to have a very good communication strategy. I am leaving, this is a very important topic, but I'm leaving it on purpose because of the topic I'm discussing. I can safely leave this out. There is no way we cannot talk about ensemble prediction and probability density. That's the way to go. Modern day prediction, this is the way to go. You want to address uncertainty, you want to see the spread of the errors, anything, you need this. But I'm leaving that on purpose for the sake of this discussion. So I'm stating that ahead. Now, we are talking of seamless prediction, but we should know that there's also seamless services. If you take just the hydro side, just take water, and there are water people here. There are so many things we can do, decisions we can make, which needs different types of information. And to get those information means we need to provide the prediction or the forecast at that time scale. You can see on this graph that the possible things that we can look at. As you go far off, we are entering scenarios. That's climate change. That's climate change issues. But there are warnings and watches, which are very short-term things, and they come out at very short-term intervals, which we need. If you go beyond hydro, we are all used to water. That's why I use water and agri. But there are many more things that needs to be made. There are decisions which are tactical, and there are decisions which are strategic. And the tactical decisions most of the time depend on the weather information. The strategic ones rely on the climate change scales and long-term scales. Those are the policy things. But in terms of management, we can have emergency management. We all know about NADMO and those people. When the storm is about to hit, you need NADMO. That's emergency management. But there is operational management which uses both weather information and seasonal prediction and not yet climate change. And that's operational. That's operational management, which is both weather and climate information. And then we also have the strategic, or the ones which use the policy, which is climate change information. So it goes beyond just water and agri. There's so many decisions that the information at different time scales are needed. That's a take-home message here. I don't know what's happening to my screen. It gets stuck. Now, having said that, we know that we can't get all what we want. We are not able to get all. There are limitations. This screen, if you don't read anything at all, just take the topic, the heading. It's all. That's a take-home message. There are practical considerations when it comes to computing and the model complexity, which will require different predictions for different scales. That's the take-home message from this. And the simulus is arguing, or is advocating that we should use a unified framework to provide this thing. Now, there's a little bit of history. This started from 2002, but it ended up in the strategic plan, the World Climate Research Program. Their strategic plan, 2005 to 2015 strategic plan, was what actually came up with this simulus prediction thing. But in actual fact, as we speak right now, the World Weather Research Program and the World Climate Research Program have it as a project. And historically, this whole simulus thing came about because historically there has been the weather prediction and the climate prediction communities. And what was missing, or what is called predictability desert, was the sub-seasonal to seasonal. So historically, when we say the simulus framework, it's the bridging of the gap between the weather prediction and the climate community. That is what it is. So the convergence has come about because it's been realized that there is no need for artificial boundaries between the different systems that are acting. The mesoscale system, the synoptic system, there's no need for artificial boundaries. It's a continuum, and we just have to factor the thing. So basically, the simulus thing has to do with sub-seasonal to seasonal. That's the historical approach. It has to do with sub-seasonal to seasonal. That is what was filling the gap between the weather prediction and the climate change, climate prediction communities. And the approach now is that the science is common. You heard Professor Amekudzi talking about they all use the same science. I'll come to that. Let me move. Come to that. Now, they all use, when you look at the models, if you look at how the models operate, they rely on the primitive equations, whether it's weather timescales or climate timescales, they use the same science. It's primitive equations. And in the simulus framework, what we are saying is that the prediction will be done with different rules, because the weather prediction problem is an initial value problem, while the climate issue is a boundary value problem. So here in the simulus framework, we are saying that the prediction will be done with both rules. The initial as well as the boundary conditions will have to be used. In terms of modeling, there is a convergence between the weather community and the climate community as far as development is concerned. And this will even help with, if you know programming, you will know that this will entail that the programming will be more involved and detailed, but at the end of the day, we have one system. Like the UK Met Office has a model which they call the unified model, and it is used for weather prediction. It can be used for seasonal prediction, and it can be used for climate change projections. So that is, and we shouldn't also forget that when we are saying seamless, it's not just about weather and climate timescales, but we have impact studies. There are people like water, agri, health, they use information from the meteorological models, and the similars can also extend to the impact studies. Now, the different types of information can be used differently. And for example, if we want, there are certain decisions that when you want to make, like you want to sensitize people about impending danger, the kind of information you use is completely different from when you are now warning them. That's a set. You are now in the middle. You are warning them that no, it's no longer about knowing it, but it's about to happen. And then now, when the thing is actually happening, that's the goal. That's the weather forecast. That's a short-range forecast. That's what you use. So similars is the decision-making cuts across scales, and that is what the resilience. That is what has to do with resilience. But the key thing is that now we don't stick to just the historical weather prediction, sub-seasonal to seasonal, and climate prediction. Now we know that there are tools and skills for even nowcasting. I mean, those of us involved in the SWIFT project, we know what is going on with the nowcasting. And the nowcasting, we all know what it is just the current state of the atmosphere and then just prediction over the next few hours. So sometimes what happens is that you've given out a weather forecast and then there's a development. The nowcasting can give you that information, even if the weather forecast is gone out already, can give you. And another new thing, which is one of the strong side of SWIFT, is the sub-seasonal to seasonal prediction, which is ongoing now. The sub-seasonal to seasonal prediction sits between the seasonal prediction and the weather forecast. And there are decisions that we can use the seasonal prediction for, like whether you should even cultivate your land this year or not. That's a seasonal prediction. You can use seasonal prediction to answer that question. But having said that, once the season starts, the intra-seasonal variability is handled by the sub-seasonal to seasonal prediction, while the weather forecast is for tactical decisions like, should I harvest, should I spray? So all these are used at different time scales, and that's the value of the similars prediction. I think I've gone ahead of myself. I've added some details here which you can read for yourself, but basically I'm just talking about the concept of similars. So the kind of things that this can be used for, what it entails, you can get it on the slide. Now, having said that, I want to show that the nowcasting, I was trying to get this. I'll give you the link because I was struggling to get it and it was not coming. There was a hailstorm on the 6th of January 2021 in selected areas. It happened in Sasabi in Accra, and it also happened on KNUST campus. The issue is that we know this is a hailstorm. We know that you can't get set things from seasonal prediction or sub-seasonal to seasonal. We know that. Even the weather forecast, I'll show you the weather forecast for January 6th. It didn't even capture this, right? And that's the value of nowcasting. That's where nowcasting comes in. This is hailstorm. This is Accra, just a section of Accra. Another one. Let's see. I want to. You see, you can get more examples. That's the same here. This is the same event. And that's the same event. So bottom line, such events illustrate or demonstrate the value of the nowcast. This is an example of a seasonal forecast. We know what it does. It just tells you above average, near average, and below average rainfall. That's what it tells you. And it's at seasonal time scales, right? This is an example of a sub-seasonal to seasonal. It gives you probabilities on a weekly time scale using certain threshold. This is just an example, one of the things. And it can give you using another threshold. This is 20 millimeters. The first one was 50 millimeters. You can even do it for 10 millimeters. These are useful for certain purposes. So every range, these are normally from S to S. Every time scale has the kind of questions that can be answered by the information. This is a weather forecast for, look at January 6th. and it never said anything about the hailstorm that we saw. That's weather forecast. It was issued on January 5th for January 6th, and it didn't say anything about it. And even the forecast which was issued on January 6th, right, didn't even say anything about it at all, right? So this is where I wanted to demonstrate that there are two useful products. You can copy this link and try it. There are two useful products, the convective rainfall rates and the rapid developing thunderstorms. I wanted to actually see to what extent it captured or what display it had over West Africa and Ghana in particular. And at least if it gave us an idea that we should expect anything. But I've been struggling with it. I got it when I did it once, and then now I tried it on my slide and I wasn't getting it. So the first one gives you a catalog of things. You will see a table and you can choose what you want and the day. And the second one gives you the products. You can see the products there directly. Now, some of the challenges. Having spoken about the different ranges, I left out ensemble prediction, but it's a big challenge. I told you that it's very difficult to talk about modeling now without mentioning ensemble prediction. One of the big challenges we have, we want to be able to have accurate weather forecasts on day one. And the way to go, the way forward or the way to go about it is to use ensembles. Ensembles are the most reliable for this kind of range, right? But the challenge is that we need high resolution ensembles and we need computers, powerful computers. So that's a challenge. Now, when you come to week one, there's still an issue with the science. There are some challenges with the science, which they are difficult to simulate. They're very difficult for the models, don't capture some of these things. The theory shows that these things are there, and the data also shows that these structures are typical structures are there, but the models are not able to capture them very well. A similar thing happens on the week 1 to month 1 time scale, but it's been seen that MJO has a very great, I think it's being used a lot now for SOS. MJO has very good promise for this time scale, and NAO is for seasonal time scale, and then ENSO is also for seasonal. So these are some of the challenges. Our ability to simulate these things will help us to predict the things better. Yeah, NAO for year 1 annual variability. The NAO is North Atlantic Oscillation. Sorry, I was using abbreviation, North Atlantic Oscillation. Another thing which has been noticed is that there is interaction between the stratosphere and the atmosphere, which can also be leveraged on for predictive power. That's another thing which has been noticed. And when you go to decadal timescales, there is an Atlantic multi-decadal oscillation and the Pacific decadal oscillation, but these are also related to the North Atlantic oscillation. And if we can really get the models to simulate these things, we can improve our predictive scale or predictive power in these ranges as well. Now, so in summary, some simulus prediction is prediction across timescales. The techniques vary according to the region and according to what time scale you are on. And the scales can range from nowcasting through synoptic to seasonal to decadal and even climate change projections. Thank you very much. Questions?
Thank you, Professor. Yeah, it's really a very good presentation, and I can see a lot of people asking a number of questions on the background. There's a hand raised. Yeah, Mr. Suman. Mr. Suman, please, can you ask a question? Hello, Mr. Suman. Your mic is off.
Oh, I didn't. Is anybody speaking?
Hello, Mr. Utuanzan, can we ask questions, please? I don't have the option of raising hand. It's not on my menu here, so.
Go ahead, ask your question.
Okay, thank you, Professor Lamptey, for that very good presentation. It's really mind stimulating. I just want to check with you, this seamless approach to modeling across time scale, it must be computer intensive, as I can imagine, and then also requiring very high level of expertise to do that. But it's very useful if, for instance, we can have that established somewhere within the GMet facility. Is it something that you think is not far from reach, that we can lay hands on in the nearest possible future? And how do you think we can go around that? Alternatively, if you consider the example you mentioned for the UK Met Office, is it a system that we can have access to and then take advantage of their computing power to sort of extract some of these information?
Okay. So, so your questions are two. In terms of, I'll start from the UK Met Office one. The UK Met Office, we need to have an agreement, like we need to approach them and have an MOU with them, and then we can have access, because there are countries who even run the UK Met Office model at the country level, but it's with a special agreement with the UK Met Office. It's not open source like Wolf. The UK Met Office model is not open source like Wolf. You need to engage the UK Met Office and come to an agreement, and then they can give you access. So that's the easy part. But in terms of the, honestly speaking, there's another model. There's another model which is a spin-off from the Wolf model. Wolf is weather research and forecasting model. There's another model called MPAS, Model Prediction Across Scales. It's a spin-off from the Wolf model, and it's trying to do, or is actually also trying to do, the unified modeling approach, like the UK Met Office does. And the difference is that the US models are open source, while the UK models are not open source. So if you have the capability to run the model, you can get the open source one and start from there. But I think in Africa, we all know the issues. We want to run the model, we need a certain minimum of minimum expertise, like we need a critical mass of people, and we need to approach it from a more coordinated effort. GMet can collaborate with a university, or GMet can spearhead. I think for me personally, it's not because I'm not being biased here, but I think that GMet has to take a certain role and pull the universities along to meet their needs. So like this modeling thing you are saying, GMet can actually lead the way and get a consortium of universities at the national scale. It's not competition. We can do it from a collaborative approach, consortium of universities or research institutions together with GMet leading, we can get it done. Abidjan, Côte d'Ivoire, they are trying to get a high performance computing. Senegal is also trying to get, I don't know whether they've gotten it now. Waskar was putting one in Burkina Faso. I have to check. I think the Waskar one is already running. But I know of these countries that are all, and even Zimbabwe tried getting HPC before. So I think that it's a matter of how we go about it, but it's within our reach.
Hello. All right, thank you. So maybe GMet can give some feedback if they have some plans of moving along, some of these directions. Is there any quick feedback from GMet on that? Or maybe they're already doing something along that line.
Okay, GMet was running a model operationally. They were running the Wolf model operationally, but there are some few challenges with it now. There are some issues that needs to be fixed on the model. The system is a bit out of date and we need to upgrade it. But otherwise, GMet is already running. Actually, we did a paper where we ran a seasonal, the Wolf model in the seasonal mode, and we compared it to the physics of the GMet model.
Hello.
Hi.
Hello. Osanza, please, can I make my intervention now?
Yes, please, sir. You can go ahead.
All right. After Prof. Amekudzi's presentation, Prof. Lamptey made a contribution and said there should be a legislation to govern the establishment of mesh stations or collection of data, if I got him right. And it's on that score I want to make this intervention. I wanted to make it at that time, but we moved to Prof. Lamptey's presentation. If you look at Ghana Meteorological Agency Act, 2004, at 682, the section 2, under the objective and functions of the agency, subsection 1 says that the objective of the agency is to provide meteorological services in the country and ensure the operation and maintenance of international standards and practices in meteorology in the country. Subsection 2 says that for the purpose of subsection 1, the agency shall, and then enumerated a number of functions, things that the agency has to do to achieve this objective of maintenance of international standard and practice in metrology in the country. Among them, especially G, says that the agency shall ensure uniform standard of observation of meteorological phenomenon in the country. And then M says that the agency shall be the sole authority to approve the establishment of meteorological stations for meteorological observations. So the legislation Prof. Lamptey was talking about actually exists. And I just want to take opportunity of a program like this to bring to the notice of the stakeholders that for you to be established meteorological stations, Ghana Meteorological Agency should be the sole authority to approve. So you can establish, but it has to be in a collaboration with Ghana Meteorological Agency, and the Ghana Meteorological Agency has to approve the establishment of the stations to ensure uniform standard of observation of meteorological phenomenon in the country. I think that's the intervention I want to make, and want to say that that legislation he was calling for actually exists, and our stakeholders should be mindful of it when they are establishing stations to collect data on the meteorological phenomenon in the country. Thank you very much.
Yeah, my hand is up. I think.
Yeah, Prof.
Yeah, thank you. I'm back from that meeting. I have closed them, so I'm here now. Yeah, so that I think it is, but you see the other issue is that how much of this information is known. So that becomes critical. So it means that for example, in KNUST, KNUST Meteorological and Climate Science Program was established in collaboration with GMet. So that has given us advantage that everything we want to do, we want to see GMet as our partners in that. So for example, in all our stations that we have set here, either we ask permission and even set it close to GMet stations so that we can do a kind of a pairing. If we take a measurement, we compare with what GMet is having, or areas that they don't have, the GMets are aware. But as to whether those data is shared with GMet is another thing. I can tell you that some of my station data, it is when GMet needs it, then they get it. So so after taking the authority to, getting permission to establish the station, GMet should also be, the data should also be made available to GMet. That is also critical. We can ask permission to seek the station, but at the end, does GMet have the data? Permission is given. So GMet should also have the data. And that is also the other thing so it's good that we have, so I believe that the information Prof. Lamptey pass was good, but we are very happy about the legislature that what has been read to us now, and then we know that we have to comply as also stakeholders.
Hello.
Hello.
Yeah, can I?
Any other contribution?
Yeah.
Yes,
I think that Professor Amekudzi said that GMet has to get the data and things like that. I think that there is a need to go beyond that. What can GMet do to make sure that any entity establishing stations or setting up a climate-related project involves GMet from the beginning? I think that's where we need to get to. Because we can say they should know or they should we should give the data, but people are doing it. We know they are just doing climate data programs and GMet is not involved. How can we get them to be involved? That's what we need. There must be some strategy for implementation. Otherwise, people are doing it. The thing is there, people are doing it. We need to find a way to implement it so people become aware. I think that's what we need to do. So the ball is in your court, GMet. We have to move to the next level.
Mr. Chairman, can I also make a contribution?
Yes.
Yes, I think so. We've all made a point of GMet having the stations or having access to the stations. But then it's a give and take affair. There's a responsibility that GMet also has to give out in taking charge of somebody's station or having access to somebody's data. If I have to buy my own station and maintain it myself, at the end of the day, I have to hand over the data to someone to use for his own professional work. I think there has to be that consideration in fact. So what contribution is GMet also giving to whoever owns the station? Probably you can maintain the station for the person. Thank you.
Yeah. Can I come in there? Oh, let me raise my hand.
Yes, Prof, you can.
Yeah, the issue is that the station, when we say that GMet should be involved or should approve it, it makes GMet a stakeholder, it makes GMet a partner. Like I told you, I don't know how many of you have seen the GMet database. We created it. There is, in the GMet climatological database, there's a category of stations called experimental stations. And you see University of Ghana, Achimota School, all those people. So that collaboration GMet doesn't just take the data. GMet maintains the station in collaboration with whoever set it up.
And if I may add a little, you see, I took this opportunity to bring it to the notice of the stakeholders that this legislation exists. We need to maybe do more to let it be out there so that stakeholders will be mindful of these provisions in the GMet Act. Let me also say that you all know and know better than I do when it comes to collection of data. For establishment of the station, there are metadata that are captured. This data must be this information must be part of the data that is collected. We are talking about meeting international standards. The data can be used for so many purposes, for research and other things. That must meet the international standard. So if GMet is approving the establishment of the station, they will take into consideration all the international standards so that whatever data that will be collected from whatever station every institution have established will meet the international standard, and it can be used for research that will be accepted internationally. And so it is in the interest of all the stakeholders to comply with this legislation. Unfortunately, it's not too much known out there. That's why I took opportunity per the interaction that came from Prof. Amekudzi and Prof. Lamptey to bring it to the notice of stakeholders that this legislation does exist and that stakeholders should be mindful of it in in establishing stations. I think our objective is not to go take people's data for not playing any role. It is in the interest for both parties to have a standardized data that can be shared. Thank you.
Thank you. I think that the information you gave is a very, for me, it's an education that we all know now, and we have to comply. And it's I think other stakeholders that have joined us, I believe that should also do same, and it's critical. And then we'll, definitely, I believe that when GMet is strong, then when it comes to issue on our research definitely will become much easier for us to do research. So we'll have to do everything possible to make sure that we have a stronger meteorological institution for the country.
Yeah, can I come in? My hand is up.
Yes, Michael, you can talk.
Okay, thank you very much. Professor Lamptey, thank you very much for your wonderful presentation. And once again, thank you to Professor Amekudzi. But I wish if any of you could throw more light on how parameterization is done and how GMet could do it. I'm bringing this out because just collecting the data and maybe keeping it for research purposes or for someone to come and buy it or make use of it. I think if the data is not collected, nobody might be responsible for it, or nobody would look for it. But if we would use it locally, then we might look for it and make sure that it is used, so that, like the event you mentioned, that there was hail, but the Met Office was not able to predict it. Like you mentioned, currently, GMet, the WAF model is not working. So we are bound to use the global models. So at least something has to be done to smoothen our forecast to suit the local conditions. So if you could throw more light on the parameterization, I think for everybody to know how useful it is, I'll be very happy.
Can I come in?
You can start, and then if there's anything, I'll also.
Yeah, Michael, the parameterization issue, it's not something that it's not something that is just based on data. It goes beyond just using the data. The parameterization issue, it's okay. Let me give you an example. For example, there are certain conditions which are valid over Accra, right? But if you go to, I'm not even going outside Ghana. If you go to Kumasi or Tamale, those conditions will be different. Now, what the parameterization issue does is, because we cannot capture all those scientific processes, you put in certain values, like you may put in for Accra, you may put in for X equals 2. Once in Kumasi, you put in X equals 4. And Tamale, you put in X equals 5, where X can be anything you are parameterizing. You see what I'm saying? Parameterizing means that you are not actually representing the physical process. You are using your knowledge or your expertise to fix a value. And most of the time, it doesn't change. It doesn't change much when you parameterize. Like that, the difference between parameterize and that's where we have, for example, let's take convection. You know, we talk about convective permitting models. They are not parameterized. You don't parameterize the physics there, the convective schemes. You don't parameterize them. You leave them to run. The full physics is running. Whilst in certain models, you can't get the full physics to run. So you have to put in some values. You have to assume certain things and fix some values in there. That's what goes on. So it's not easy. It's a whole team that does it. Because whatever you are putting there, you have to test it. You have to go back, you run it a big test, that small part alone before you run it with the whole model. It's a whole thing. It's done by model developers.
Hello, now I'll take 1 minute to read it.
I want to add, I just want to, so as he has said, so these kind of things, it really require a lot of research. It's only about, because you are talking of equations and that you really need a lot of testing and etc. And some of them, so it's there's a lot of simulations and continuous simulations. You test and make this and implement it and so on. So I believe we will get there. So long as we are, but definitely soon you have a research, you have nothing than to have like UK Met office. You have a group of people, possibly they might have finished their PhD. 1 year, they might have only grants to come and then do research at your institute. All that they have to do is to really work on some of these processes. Until we get the critical mass, it's impossible to really get there. So that is what I want to add. Thank you.
Okay, I want to read the chat so that
thank you.
Those who... Hello, Martin, you want to say something? Hello? Hello, Martin. Okay, message coming from Michael Bedu. He says, just as Prof. Amekudzi suggested, GMet can provide the universities with the limitations they have identified with the rough simulation that need detailed research. I think Dr. Amekudzi addressed that. Then this one too is coming from Delali Duvier. Please, Prof. Lamptey, you are talking about GMet having consortium with others, but are the units or division within GMet itself very well collaborating among themselves to build a strong synergy within before even stepping out? Please help me, and I want to be candid. Another from Emmanuel Obuobi. The seminar has been wonderful. Thanks to Prof. Amekudzi and Prof. Lamptey. From Michael Bedu, I'm sure GMet has a research department which is already doing various studies with the data and publishing these results. This department can help make maximum use of the data being collected. If further expertise is required, a good collaboration with the university should take care of this. These are the information from the chat. Thank you for a nice presentation. I think we've benefited from both expertise, and this seminar is something that will come very often. Next month, we will also invite another expert to talk on various topics pertaining to weather and climate, not only the scientific aspect, but the social aspect too. So it's not only between GMet and KNUST. I think we are open to all institutions. It's not only about GMet and KNUST. We just want to bridge the gap between the academia, the users, and the service providers. I think in all to better the country's needs. Yeah, all suggestions will be working. Thank you very much. If we have anything, Prof. Amekudzi and Prof. Lamptey, you can add so we can close the seminar. It's almost 1 p.m.
Sorry, can I please ask the question?
Okay.
I was asking Prof. Lamptey that with his experience in seasonal forecasting, modeling, working with modeling, my question is that how well do they usually use this, especially these Atlantic oceanic indices in the seasonal forecast? Because usually the focus is on using these ENSO indices because of the global interest in ENSO.
Yeah, the signal from the NAO is not as strong as the ENSO. The ENSO signal is really very pronounced. So when you say seasonal forecasting, the first thing that comes to mind is ENSO, because that is what has been proven. But there's some promise from the NAO. It's not very strong over the tropics, but it's shown some promise, and I think even the interaction between the stratosphere and the troposphere has also shown some promise. But some of these things are being seen on different time scales compared to the seasonal. As for seasonal, it's ENSO. It's ENSO. ENSO is the strongest signal for seasonal prediction.
Okay, so we can look at some of those indices on the sub-seasonal time scale.
Yeah, MJO is very good for sub-seasonal. And you can try to improve the seasonal by looking at these other things like NAO and what it's saying and all that. In addition to that, ENSO is number one, but in addition to that, you can try to look at NAO.
All right, thanks.
Yeah, so there's no other thing. I also think that it has been a successful seminar, and thank you all for coming.
So see you next month.
Yeah, bye.
Thank you.